So today we'll be discussing lecture 15. I'm not sure whether you got a chance to go through it or not. And the lecture is mostly about three things. One is reviewing some of the things from the previous lectures, mainly decoding and beam search. And then the rest of the lecture is about natural language generation and dialogue systems. So let's go through the slides. Towards the end of this session, I would be showing some example chatbot data so that you'll get to know how the data looks like when you're working on developing a chatbot. So the first few slides are about some announcements. So this is the overview of today's of this lecture in today's session. It's mainly about what's been happening in NLG, natural language generation. We'll see what that means. And we'll also be quickly discussing decoding algorithms and how can we evaluate NLG. How do we evaluate NLG? So we'll get started with recap of some of the things that were discussed in the previous lectures: language models and decoding algorithms. So, what exactly is natural language generation? Natural language generation is an NLP task in which you generate text. You must have come across blogs or some Twitter post or some course or some session or any video where you must have heard about natural language generation. It could be something like we now have the abstracts of the research papers are being generated, and then we have poetry that is being generated. We have music lyrics that are being generated. So all of these come under natural language generation. So it's not just the creative or the art side of it. When we're talking about language generation, even we have that in machine translation as well. So in machine translation, we have text in source language, which gets translated into some target language. And even there we have language generation as a subcomponent. And then we have summarization, in which, let's say, we have an article or we have some document, and we want the machine or the model to generate a summary of it, which is nothing but a brief summary of it in few sentences. And then there is language generation in dialogue systems as well. We have all these virtual assistants or any kind of chatbot applications where you try to talk with the bot. And even there we have language generation. And then we have NLG in creative writing, like storytelling, poetry generation. And we also have free-form question answering, like, so we have Squad dataset, which is Stanford's Q&A dataset. But what actually happens there is that you're training a model which is kind of extractive. So what does it mean when we use the word extractive? It means whatever the responses or the outputs that a model generates, it is not really generating something it hasn't seen before. Rather, it's more like it is extracting information from some sort of knowledge base or text. So that's called extractive method. And the opposite of it is abstractive, where the model tries to generate text on its own rather than extracting information or responses from some knowledge base. So that's free-form question answering. And then we also have image captioning, where you give an image to the model, and then the model generates some sort of captions to the image. You must have seen this somewhere on the internet. So what is the language model? So the language model's task is simple. Given a sequence of words, it tries to predict what comes next. So that's what a language model does. So when you're using something on your mobile and you're typing something, you see word suggestions coming at the top. So that is done using language model. So what it does is it takes the words it has seen so far, the previous words or the words until the current timestamp, and then it tries to predict the next word conditioned on the previous words. So that's what we see here. YT is being conditioned on all the words that have come before it. And so it it is dependent on the probability distribution, and language model produces this probability distribution. So language model is not something which is very specific to RNNs. It has been there before, as before the deep neural networks have come in. So when we are using RNNs for it, it gets called an RNN language model. So conditional language model. So the model has seen some words so far, and then it tries to predict the word that comes next. It tries to predict the best match, the closest one possible. And so that's what language modeling is. And what about conditional language modeling? So here, conditional language modeling tasks can be like machine translation, summarization, dialogue. These are some of the examples. So how exactly do we have conditional language modeling in machine translation? So here in machine translation, the output is conditioned on the source. So you get a source sentence in some language, and conditioned on that, the seek model or the machine translation model generates a target sentence which is very specific and dependent on that input sentence. And then we have summarization, which is another task. It takes some amount of input text, and then it generates a summarized text of the source. And we also have dialogue, where we give the model a history of dialogue, some past conversations, and then the model has to predict what to say next, the next utterance. So these are some of the examples of conditional language modeling tasks. So this is how a RNN language model looks like. Here on left, we have the encoder, where the source sentence, each word of the source sentence is passed through an RNN unit, and the output from the encoder is given to the decoder, and then the decoder produces one word for every input word. So this is what you must be familiar with this if you have gone through the previous lectures. So what are decoding algorithms? So when you have language model, which is so what language model tries to do is it tries to predict the next word given some words. So it uses few things when it does that. So a decoding algorithm, so as we have seen here, the decoder is what is the component that generates the actual output. It produces or generates text. So it does that using several decoding algorithms. One is greedy, and the other one is beam search. We'll see how each of these differ. So when it comes to greedy algorithm, what it does is at every timestamp, it just produces the most probable word. So this is what happens in softmax, right? So when you have to give a simple example, when you have cat versus dog classifier, or let's say cat versus dog versus lion or something like that, and finally the softmax produces three outputs, and then you take a argmax. Argmax is nothing but you get the highest highest probability score, and that's what your prediction is. So that's what greedy decoding does. It simply goes through the probability distribution that is generated by the language model, and then it blindly picks the most probable word, the one with the highest score. So that's what greedy algorithm does. But the way it works and the kind of outputs it produces, it's not really that good. The output can be poor. Especially it could be ungrammatical, it could be unnatural and nonsensical. We'll see some examples of this. And the other way of decoding is beam search decoding. This was discussed in the previous lessons. So what it does is, instead of simply throwing one the most probable word as the next word, what it does is beam search uses multiple hypotheses. So it has something called beam size. K is the beam size, and K varies, like it could be 1, 2, 3. So, and then there is some stopping criterion which is set, and depending on that, your beam search is going to decide what comes next. Here is an example. Let's say that at each position here the size k equal to 2, which is why we see the branching is like the branching is two-way. If it is 3, we will be having another path here. So let's go through this example. What we have here is, let's say we have the word he. We got started with the word he. Then the model would generate two hypotheses. The next word could be hit, or the next word could be struck. And then it goes through each path. Like let's say the first word is hey, and the model thinks with score of minus 1.7 that it's a hit, and it thinks that the next word could be struck as well, but it has a lower score here, as we can see, negative 2.9. So it takes the word hit, and then the next word could be a or me, and me has higher score here, so it goes with that. So it follows like this, considering multiple hypotheses. So finally, the sentence that we have here indicated in blue is, he hit me with a pie. So this is how beam search works when k is 2. So this slide is about Westworld. If you're not familiar, I mean, if you haven't heard about it, Westworld is a TV series. I have seen few episodes of it, and it's quite interesting. And the course, the lesson instructor today has taken this, showing that maybe this here, what she has seen in some episode of the TV series is that she thinks that this is a beam search, and she has this is a knowledge base, and then there is forward chaining and backward chaining, which is nothing but forward pass and backward pass, and then there is some fuzzy logic here. So she has nicely referred this to the things that we discuss in neural networks and NLP. So what happens when we change the size of the beam search? Like when we change the size of k, what happens when we increase it, and what happens when we decrease it? So if k is too small, like when k is equal to 1, then that means we are again having the same problems as that of greedy decoding method. We'll be getting results which are not really good. So that's what happens with smaller k. So when we go for larger k, it does help in overcoming some of the problems that we have with greedy decoding or with smaller k. But it comes with some sort of trade-offs. One is that as you increase the k, you have to do more and more computations. That's clear, because as we can see here, if what we see here is a simple example with beam size k equal to 2. If k size is much bigger, we can see that the number of hypotheses and the number of alternates would be much more, though there would be though there will be some sort of terminating configuration, yet this would lead to higher computations. Sorry. Yeah, so larger k means that it is computationally expensive. And besides that, increasing k also has other problems. It has seen with experiments that if the k is increased too much, that leads to decrease in blue score. So blue score is one of the methods of evaluating some NLP tasks, like machine translation. So if k is increased, it is noticed that blue score decreases. And why does that happen? It is because for larger k beam search, the outputs that are produced are short translations. So that's not something that it's not something which is good. So if k is increased, the results produced by the machine translation model are short. So that's not good. And another problem is that if larger k is used for decoding in tasks like dialogue systems or chit-chat systems, the results that are produced are more generic. What does that mean? So here, as we can see, we have an example sentence on the left here. I mostly eat a fresh and raw diet, so I save on groceries. So this is some example sentence. And the model response for this is that I love to eat healthy and eat healthy. That is a good thing to have. So there is some sort of trend going on here. If we see the top sentences, they are related to the topic, current topic in discussion. So here the input sentence is talking about food, about something related to eat and health. So as we can see here, at least the first sentence is something which is very related topic wise. As we go down, we see that the sentences are more generic. What do you do for a living? Now that got it could be somewhere related to our to the input sentence, but it's not really. So these are more like generic. At the top, we have sentences which are related to the input, but they're not really they're not really structured with good English. So that's the problem. So when we have low beam size, what happens is the responses that are generated are more on topic, but they're nonsensical. If we're going with higher beam size, what we get is we get more safer responses. Now, why are we even using the word safe here? Now, if we are building a chatbot or some dialogue system, if the system in place can't really understand what the user says. Now, let's say you open your Google Assistant and say something which the model can't recognize. The model has to fall back to something which is safer or something which is okay for the user to hear from the virtual assistant. So that is why as you increase the beam size, the model produces outputs which may not be totally on topic, but are safe and generic. And another decoding method is sampling-based decoding. What happens here is that, again, we have two types here, pure sampling and top-end sampling. In pure sampling, for every time step, like for every state of the decoder, the sampling happens, right? For the decoder produces one output for every, one output for every hidden state. So what happens there is that instead of going by the argmax to say, instead of going and picking the word with the highest probability score, what happens here is that they do a random sampling. So they take the probability distribution and do a random sampling out of it, and that would be the generated word for that timestamp. So so this is very much like greedy decoding. Sorry. But instead of using argmax, we are going by random sampling. Now that's how pure sampling works. When it comes to top-end sampling, what we have is instead of going totally for random sampling, the sampling is restricted to some top and most probable words. So this way, excuse me. So this way what it does is the model, this way we are confining the outputs to be one among the most probable words rather than making it totally random. So top n for different values of n, when n is equal to 1, it is nothing but a greedy search, because when n is equal to 1, we are picking the most probable word, and that's nothing but greedy search. And when n equal to v, that's where we have the pure sampling. So depending on the task, let's say if the model that we are working on, the task of it is to generate more generic and safer outputs, then it's better to go with lower n. That way we'll get outputs which are safer. They may not be totally on topic, but they will produce safer outputs. If you want more diverse outputs, which are more related to the topic, then you can increase n. So that's all about the decoding algorithms. And there is something called Softmax Temperature here. I didn't read more about it, but as we can see here, it is some variant of Softmax. What it does is if the Softmax temperature is increased, we get more diverse outputs. So it's like the kind of probability scores that are generated, rather than assigning one high score for one word and lower scores for the rest of the distribution, what it does is having higher softmax temperature, it gives you more like a uniform probability distribution. That way, your model doesn't really produce the same kind of outputs, or let's say it doesn't confine itself to very limited vocabulary, but it's more like uniform and more diverse. But when the softmax temperature is decreased, what we get is the output is concentrated more on top words. It's more like, again, like picking the most probable word. Here's a summary of what all we have discussed about decoding algorithms. We have greedy decoding. It's simple. It simply it gives low quality output, but it's more on topic. And then we have beam search, where it uses multiple hypotheses. And then we have sampling methods. We have softmax temperature. Softmax temperature is not really a decoding algorithm, but it's just a method to control how diverse the outputs of your model need to be. So that's all about language modeling and decoding. Next, we have NLG, natural language generation. We'll see how NLG has evolved over the years. So what exactly, so one of the tasks of so summarization is one of the tasks that uses NLG. What it does is it takes some input text and then it writes a summary for it. So this summary is usually much shorter than the original text, and it has to contain the main information from X. So it could, there are different settings in which it could happen. Like, let's say you have a single document and then you want to write a summary for it. That's a single document X. And then you generate a summary Y for it. So that's different from a multi-document, where let's say we have an article that is multiple pages and multiple documents, and then you want to write a summary for it that covers the entire article. So that's multi-document. Normally, when we're talking about either it's single document or multi-document, what we have is there is some sort of overlap in the content across multiple documents. So that way the model summarizes it over all the documents. So here are some of the datasets like Gigaword, LC, STS. And then as we can see here, sentence simplification is another task. What it does is it tries to rewrite the source text in a much simpler way. Now, let's say you have some text and you want to simplify that so that even children could read it. Can you all hear me?
Yeah.
Oh, okay. I thought I logged out of Zoom. Okay. Yeah, so that's about sentence simplification. You take an article and try to rewrite it, making it much simpler for people to read. So that's another summarization task. So there are two main strategies for summarization. One is extractive summarization. The other one is abstractive summarization. So what is extractive? So in extractive summarization, what we have is the model tries to simply collect information from the text corpus, like collect some parts of it, put them all together, and give out the summary. So that's what we have in extractive summarization. When it comes to abstractive summarization, what happens is the model generates new text rather than simply copying the text or paraphrasing from the text corpus. So this is more generative than extractive summarization, and it is also more difficult and more challenging. So this slide is about how summarization used to happen before neural networks have come in. as we can see here, we have a pipeline here. We have different components. We have content selection, we have information ordering, and then sentence realization. So what does each of these components do? So when it comes to content selection, let's say we have collected some n number of documents and we want to train a model on it for summarization. We have to do some sort of content selection first. It's not like we'll simply dump all of the text that we have collected into the model. So we have content selection, which selectively chooses some sentences which the model feels will be helpful for the training. That's about content selection. Then information ordering. So the sentences or the text that the model has chosen or the pipeline has chosen during the content selection, they have to be ordered. And then we have sentence realization, where some parts of the selected text could be removed and some of the things could be fixed. So these are the different components that were there in the pipeline of summarization. So coming to each of these, content selection uses sentence scoring functions. So content selection is all about selecting what content to train the model on. So one thing that it uses is something called sentence scoring functions, where for each of the sentence that it has collected, it tries to give it assigns a score for it. And it could do that in different ways. One is maybe it will simply search if there are any keywords present in the sentence. So if those specific keywords are present in the sentence, maybe that assigns a high score for that specific sentence. This component could also use something like TF-IDF, the term frequency, which is quite common in NLP. And another feature could also be where exactly the sentence appears in the document. Normally, when you have some document, when you're reading through it, maybe the sentences which come at the top have higher score than those that come in the middle or the bottom. And then we also have some sort of graph-based algorithms, where every document is, the documents are seen as a set of nodes, and the edges between the nodes tell you how similar the sentences are. So that is also used for sentence selection. So that's about summarization of how do we evaluate it. So it was mentioned several times during the lecture that evaluating summarization is not at all easy. So there is something called Rouge. It's pronounced as Rouge. And it is again like blue, it uses some sort of n-gram overlap. So when it comes to tasks, anything with NLP, one of the ways of evaluating is that you have the label data or the expected outputs, and then you see some sort of n-gram overlap, and you can score it. So Rouge does something like that. Rouge is based on recall. There's a difference between Rouge and blue here. Rouge is based on recall, whereas blue is based on precision. The reason being that precision is more important for machine translation, whereas for summarization, recall is more important. However, it's not like the reason why it's mentioned that evaluation of summarization is not easy. That's because even these metrics are not really helpful, not totally helpful, not all the time. Again, another difference between blue and Rouge is that blue is reported as a single number, like whatever the n-gram that you're considering, it combines them all together and then it outputs a single number, whereas Rouge reports separate scores for separate n-grams. So Rouge 1 gives a score for unigram overlap. Similarly, for 2, it's bigram. And it also has something called longest column subsequence overlap. So here is an example of a summarization. What we have here on the right is a much bigger text. Is there any question? So someone is not on mute. Thank you. So what we have here on right is a longer sentence. And we see here that it is being summarized as a much shorter sentence. We have Russian Defense Minister Ivanov called Sunday for the creation of a joint front for combating global terrorism. And the summarized text for that is Russia calls for a joint front against terrorism. So we can see that this summarized text is very relevant to the original text. And this is generated using neural networks. So now we are talking about neural summarization, which started something like 2015. And sequence-to-sequence model was used. There is this paper called seek-to-seek summarization paper. So just like other NLP tasks, even summarization has seen a lot of development since 2015 or so. One thing is making it easier to copy. So what does it mean, the word copy here? So if you remember, when we were going through machine translation, there were examples where some of the words in the source sentence were simply copied as it is into the target sentence. So that's something that happens. So the copying has to be easier to happen, and also the model has to do it only when it's necessary. So it should make sure that it is preventing too much copying. If it simply copies things from the input to the output, then we wouldn't really have good results. So there are also some improvements in hierarchical or multi-level attention, and even reinforcement learning is being used. There is one slide on this about how using reinforcement learning has given better root scores. Yeah, copying mechanisms. So the seek-to-seek with attention systems, they can produce fluent output, but they are bad at copying details. Like if there is any rare word in the input sentence, they can't really copy it correctly. So that's a problem that we have seen in machine translation as well. So in the copying mechanisms, the system tries to copy the words from the input to the output. This is useful for summarization, and yeah, so the difference between extractive and abstractive is that, so what we need is more of a hybrid approach. We don't want the model to simply extract text from the text corpus, and we can't expect the model to be totally abstractive as well, because then the model has to generate text all the time, which may not be always possible. So what we need is more of a hybrid approach with a combination of extractive and abstractive methods. And this also helps in copying phrases, the rare words and phrases. Here are some examples of some papers. These are about copy mechanisms. Yeah, and here are some problems with copying mechanisms. If the model is trying to copy too much, let's say there are some long phrases and even some whole sentences that are copied from the source to the output text, then the model is not really being much, it's not doing much for us. So in that case, if the model is simply copying text from the input from the source to the target, then it's simply being is an extractive system when it's supposed to be an abstractive system. So another problem is that if the input document is too long, even it impacts the content selection. So that's another problem. So when it comes to content selection, as we have seen in the pipeline, before neural networks, what we had was that we had separate stages for content selection and realization. Whereas when it comes to the neural network methods, all of these things are more like clubbed together. They're mixed together. And for every step of the decoder, the content selection is done. Though it is not really good, because that way no global content selection strategy is present in the system. The fix for this is bottom-up summarization. What is that? So as we can see here, there are two phases here. One is content selection phase, other one is bottom-up attention stage. So here we have, on left we have our source text, and then we have something called masked source. So what happens here is that in the content selection phase, the source text is taken and that is passed to a sequence tagging model. So sequence tagging model is nothing but a sequence labeling model. So depending on what it is trained to do, what it does, it goes to the text and it kind of tags or labels the words. So here in this case, what it does is it goes to the text, and for every word it says, it puts a tag saying include or don't include. Now, once we have the masked source where every word comes with a tag saying include or don't include, that is being used by the bottom-up attention stage. And here what it does is when the seek-to-seek plus attention model takes this as its input, if it sees a word with the tag don't include, it will not include that in its summarization. It will not use it for summarization. So this way what we are having is we have a better content selection strategy, and also the copying mechanism that happens here, it doesn't really copy long sentences or long phrases. It is kind of constrained to shorter words and not long words. So that way what we get is more of an abstractive output than an extractive output. So these are some results about what happens when what they have noticed when they use reinforcement learning. As we can see here, using reinforcement learning instead of ML has produced better root scores, but the problem is that they didn't do that well for human judgment scores. But as we can see here, while ML has 6.76 for readability, RL has 4.18. But what's interesting here is that the hybrid model, ML plus RL, has produced the best scores here, the best score here, 7.04. So now we come to dialogue. We have discussed summarization so far. So we'll go through dialogue quickly, and then I'll show you some example of how to build some example data, like how it looks to train a dialogue system. So when it comes to dialogue systems, these are nothing but the virtual assistants that we have, the chatbots that we have, they're all dialogue systems. They could be task-oriented, something like assistive, very specific, let's say customer service. If you're using Amazon, the way the Amazon chat works right now, it's different from how it used to be like a couple of years ago or a year ago. Right now, previously, whenever you go for Amazon chat support, you're directly you get linked to some person. But now what happens is you first talk to a chatbot, some dialogue system, and then if it fails to help you, then you're passed over to some person. So you can use it in customer service. You can use the task-oriented dialogue systems for giving recommendations, for question answering systems, and tasks like that. And they could also be used for something like cooperative, where two agents try to solve a task together, or adversarial as well. And the other type of dialogue systems are social dialogues, where simply they chit-chat things like virtual assistants, and also there is a lot is happening in the area of chatbots. They're not just being used to answer frequently asked questions, but they're also coming up with chatbot apps for social and mental well-being as well. So now this is about a comparison between pre and post neural, like how the dialogue systems were before neural networks and after neural networks. So the dialogue systems could be categorized into two. One is closed domain and an open domain. When we're talking about open-ended or open domain systems, we're expecting that dialogue system to answer any question that the user asks. So that's not something that is really possible at the moment. But whatever we have right now, they are kind of not so open-ended. So even when we're talking about Alexa, Google Assistant, and all these things, they're actually trained on a lot of text corpus and dialogue conversations, but they are still not open-ended. So before the neural networks, it was more of, there used to be some sort of predefined templates or some sort of corpus of responses. So whenever the user asks something, the system gives a response from the closest match. So that's how it used to be. And since 2015, with neural networks coming in, it has changed a lot. So now we are using sequence-to-sequence based dialogue systems, but even with this, there are a lot of problems. So even now, with whatever the NLP developments that we have seen, there are still a lot of problems. Rather than saying that we have a lot of problems, it's more like it's quite it's really hard to come up with let's say a dialogue system that can answer any question that the user asks. There are even a lot of competitions. Even Alexa has a competition on building conversation systems. So yeah, so here these are some of the problems that we have with the current dialogue-based system. One is genericness or boring responses. So the way these dialogue systems are developed, even if you have used Google Assistant, you must have experienced that when you say something which the model can't, which the app can't really understand, it simply says, sorry, I don't know that, or something like that. That's because there is something called fallback mechanism. So when the chatbot can't really figure out what to answer, it falls back to some safer response. So that way the dialogue systems could produce boring responses, and they can also give out irrelevant responses. When, let's say, you asked about weather, but it tells you about food, so that's a relevant response. And then they could also get repetitive, like they could get into this endless loop of saying the same things again and again. And there's also lack of context. Let's say you asked your dialogue system something, and maybe like 5 or 6 exchanges later, you ask something that is related to that, but it fails to answer it because again it can only remember few things from the history but not all of it. And lack of consistent persona. So persona is like when you're talking to your virtual assistant, uh, you, especially with these things becoming more and more usual with people using them, persona is a very important thing. Like when you're interacting with a virtual assistant, you want that to be you want to make it feel like it's some person. So you want to add some sort of consistent persona to your dialogue system. So irrelevant. So these are some of the problems. So one of them is irrelevant response problem. So the dialogue system that's trained using some seek-to-seek model, it could produce some unrelated utterances. So it's something like when you say something, it could say something like, I don't know, these kind of responses. So to avoid that, there's something called maximum mutual information. I haven't really dipped into it, but yeah, so it's something that you can use to optimize the outputs that are produced by the dialogue systems. And then coming to the boring responses, if let's say we have a very domain specific chatbot and all the time it is giving you generic outputs, which means there are some rare words which are very domain specific, but the model is never really producing them, then one way of fixing that is to upweight those rare words during the beam search, so that the beam search uses its hypothesis to produce these upweighted rare words and generate them. And another way to fix it is to use a sampling decoding algorithm rather than a beam search. And train a retrieve and refine model rather than the generate from scratch model. So what does this mean? So instead of expecting our model to totally generate text from scratch, generate text on its own, maybe we can design them in such a way that they can take some responses which are already there and then refine them so that they look more human-like and interesting utterances. So this is what happened currently when we are using, if you use any sort of chatbot frameworks, this is what happens. You give the model some sort of utterances, and even when you say something which is slightly different from this, the models would be able to refine them and pick them up. We'll see some examples for that if we have enough time. So there's another problem with repetition. So this lack of consistent persona, these were all skipped in the lecture. So coming to storytelling, this is another NLP task. Storytelling is where you try to generate a story like paragraph, given an image. So that's one way of doing it. Or you're given a prompt and then you have to generate a story for that. Or maybe you're given something, you're given a story and then you have to continue from where it's left off. So these are all some of the tasks that are related to storytelling. So here's an example. the model is given an image and then it has generated this text. So this is the image and it says you have to be the only light bulb in the night sky. I thought, oh God, it's so dark out of me that I missed your promise. So what exactly is happening here? So this image is generated from this model. I think I missed it somewhere. Yeah, so what they have done is they have used some, I think it's Coco dataset, which has images with captions. They have generated the embeddings for the captions, and then they have also used Taylor Swift lyrics with that model. And this way you can see that the text that is generated are more like the lyrics of a song or something. Yeah. So the Coco dataset is used, and the encodings are generated for the captions, and then using Taylor Swift lyrics, and they trained an RNN language model that generates text based on this. So these are all some other examples. These were not really discussed in the lecture. Evaluation. There are some problems with word overlap. They don't really produce. They don't give best results when it comes to evaluation. And another problem with Rouge is that Rouge awards, we have extractive summarization and we have abstractive summarization. Somehow Rouge rewards the extractive summarization more than the abstractive systems. Perplexity is another metric. Yeah, so I want to quickly go through this slide. So there is a problem with these evaluation metrics, whether it's perplexity or whether it's Rouge. They're not really, they don't really give the best way to evaluate our NLG tasks. But what we can do is we can use some sort of automatic metrics like fluency. Maybe once we have some text generated, we can use some sort of language model to check how fluent the text is. And we can also check for something like style correctness. We can check how diverse the generated text is, like how often the rare words are used and how unique the engrams are. And we can use these sort of automatic metrics in addition to the other evaluation metrics. So human evaluation is still considered to be the golden standard for many NLP tasks. But the problem with this is it's very slow and it's quite expensive. Even if these two constraints are met, even if it doesn't matter that the human evaluation is slow and it's expensive, even if it's fine, there are other problems. One is the humans are inconsistent. There is very high chance that the same person, if he's given to evaluate the same text, he might do it differently at different times. So inconsistency is a problem. Being illogical is another problem. Concentration, misinterpretation. So these are all the problems that come in when we are having humans in the loop for human evaluation. So what we can do is if you're using human evaluation, what we can do is we let them talk to, let's say, some dialogue system, and then we get some metrics like how well did this conversation go, how engaging was it, and these kind of questions can be answered to kind of evaluate the systems. But again, the problem with this is that these are very subjective. It changes from person to person, and the person, and also there is different expectations. Like one person might have a totally different expectations from the other. So that's another problem. So these are some of the metrics. One is humanness. How human did the conversation feel, and how engaging was it? It could, right now, whatever the chatbots that we have, it is possible to make them engaging, but it's not really possible to make them human, because if we're able to do that, it means that we are actually passing Turing test, which is not really possible at the moment. And here's another slide. Yeah. So the more open-ended the task is, that the harder it is. So this makes sense, because if we're expecting our chatbot to answer anything that we ask, then that's not really easy to model such a system. So open-endedness is is still it's still a hard problem, and trying to make the model trying to make these kind of systems generalized is not really possible. Rather than that, maybe we can aim for specific improvements. That's much better than trying to improve the overall generation quality. And if we're going for human evaluation, the questions that we use to evaluate the system should be very focused, so that they kind of get the proper answers from the humans that do the evaluation. Reproducibility is another problem. Working in NLG can be very frustrating, but it is also very funny. That's very true, because if you happen to work on any sort of dialogue systems, there are some unexpected outputs that you get which would definitely make you giggle. And this slide was shown at the end of the lecture, and you can hear people laughing and giggling towards the end of the lecture. You can go through the slides, and we still have like 4 minutes left. I want to quickly show some data chatbots. I hope you all can see the browser now. Yeah.
Yeah.
Okay, thank you. So here is some training data. Let's say you want to build a bot for weather. You say something like hi, and then it responds, and then you ask how's the weather. So the training data looks something like this. You first prepare some sort of examples like this: hello, goodbye, what's the weather in Berlin at the moment. These kind of examples are all collected together, and then for every sentence there is something called intent. So when you're saying hello, you're actually greeting the bot. So you have to say that, okay, it's a greet intent. And when you're saying what's the weather in Berlin at the moment, you're actually asking for some information. So that's an inform intent. So this way you actually put together data like this. And this is very simple. It's just for a simple weather bot, and you can see how much data that you have here. And once you have this, you also need to give the model some sort of dialogue history, conversation history. So what this means here is that if the greet intent is, if the model predicts a greet intent, it has to do utter greet. So what is utter greet? Utter greet is nothing but the response that it gives. Hello, how can I help? So when the user says, hey, the model would say something like, hello, how can I help? So this way you actually have to prepare your data. So this is for the chatbot building platform Rasa, but more or less the data looks the same. Even if you go for Dialogflow, or even for Dialogflow, it has Google's Dialogflow also has a similar structure. So this is about the dialogue systems. Maybe we can go through this in the next session in detail if it interests you. So we only have 1 minute left. If there are any questions or anything that anyone wants to add, please do. Are there any questions? Okay, Srinivas has shared some good resources for understanding attention better. That's a very good list. Go through that if you need help with understanding attention and similar things better. So that's about today's lecture. Then, if you have anything that you would that you have come across and that help you understand something better, please do share that in the channel. And if you want to add something of your own, like if you want to discuss the assignment or something that you have read in any of the next sessions, please do let us know. So if there are no questions, or if there is nothing anyone wants to add, I think we're already at yes, so we are done with our time today. Thank you all for joining today. Have a happy weekend.